Our next speaker is a research associate from the University of Bristol, Kyriakos Georgiou. He's actually speaking about some research we did, TBS did with the University of Bristol regarding coverage models for multi-threaded programs, and also done with XMOS. I think some of the XMOS people are here as well. So I'm going to hand over to Kyriakos.
Thank you, Mike, for the introduction. So this is the overview of my presentation. It's split in two parts. First part is the proposed coverage model, and second one is a case study to evaluate it. So in a study conducted by Peterson on message passing programs, communication-related bugs were the most common to cause runtime errors with a shared 25%. And conventional coverage models are inherently weak to capture those, to exercise concurrent scenarios. So we came up with a coverage model which provides coverage tasks to ensure that the correct communication in a message passing multi-threaded program. The coverage model consisted of 7 coverage criteria introduced in a hierarchy, and the coverage criteria were incrementally capturing all the aspects of the communication in the program. And it is important that bugs were actually, we were able to capture bugs statically prior to running any test due to its expressiveness. So in this figure we have the 7 proposed coverage criteria alongwise with their hierarchy. And the meaning of the hierarchy is that any criteria in the upper level covers all the criteria in the lowest level. So for example, if you creating coverage task for criteria 4, criteria 2, 3, and 1 is covered. Now, criteria 1 is extracting the channels of the communication in a program. Criteria 2 has to do with the send statements, criteria 3 with receive statements, and then criteria 4 is the Cartesian product of 2 and 3 on a particular channel. So it's a send statement with a corresponding receive statement, which is doing a synchronization event. Then you have criteria 5, which is a sequence of synchronization events in a particular order. Then you have criteria 6, which is in order scene events, which it take into consideration both reaching first in the execution the send statement or the receive statement. And then you have the criteria 7, which is in order-based scene sequences, which take into consideration the scene events in order. We are omitting in our case studies the 2 last criteria because we are dealing with a synchronous blocking message passing model, which we don't actually care which event was reached first. And what we are targeting for having the conditions for having a bug-free program for scene events and scene sequences is for all valid scene events and scene sequences to be feasible, and for all invalid scene events and scene sequences to be infeasible in our code. So we are testing again feasible scene events and scene sequences. Then we propose two methods to extract coverage tasks. The first is based on code coverage criteria, which we are trying to extract the coverage task for send statements, receive statements, and channel. And we are doing that by simply traversing the abstract scene tree created from the front end of the compiler and extracting all the relevant nodes to those 3 criteria, so channel, receive, and send statements. And after we do that, we can form the Cartesian product of send and receive statements on a particular channel to get the synchronization events. And secondly, we extracting coverage task for structural coverage criteria, which is essentially the synchronization, the scene sequences. And how we are doing it is by use of the event interaction graphs proposed by Kadayama. What is an event interaction graph? So it's a graph composed by event graphs for each thread or process, and then the interaction between them. And the interactions are also scene events. So we again traverse the abstracts in that tree, and then we create the event graph for each of them of the threads, and then we also produce the interactions. Then we traverse that graph in order to extract all the feasible scene sequences. And it's important here to say that due to lack of semantics of the program, you always need some, probably you will need some user input to identify all the feasible scene sequences or the feasible scene events, because by static analysis, you can control flow analysis, you can come up with some cases that are not feasible. So now regarding our case study, we use XMOS XC Language, which is a concurrent real-time language intended for the XMOS multi-threaded architecture. XC applies a message passing paradigm for communication between threads on the same core or on different cores. And communication is achieved over channels where each channel provides synchronous point-to-point connection between the two threads. So what we did, we create a bug-free program, and then we introduce bugs in that communication-related bugs in that program, and we try to evaluate our coverage model using it to create coverage task on that program. So here we can see the initial version of the program without any bugs, and on the left side is a event interaction graph. We can see that we have 4 threads, and there is a lot of communication going between those threads. And on the right side, we can see all the scene sequences, so it's which are valid, and they are specified by the communication protocol of the program. So these are the valid sequences that can happen during all the possible execution of this program. For example, if you take sequence 1, event 1 should execute first, then event 2, then event 4, then 5, 7, and 8, and then the program should done. Then we introduce our bugs in the code, and it's important here to say that we introduce them in such a way that the program still, with the same input, can execute it without hitting any bug or without stalling. So after introducing the bugs, we run the first method of extracting the coverage task, and we extract the coverage task for channels, send statement, receive statement, and scene events. So channels are the channels in the program in the first column. Send events are the send statements on a specific channel on a thread. Receive statements are the receive statement on a specific channel and on a specific thread. And then we have the Cartesian product of the second and the third column, which is creating the synchronization events. In the 2 events that are dark gray colored, it was 2 events that the user identified that are not feasible to happen during any execution due to the semantics of the program. So if I go back, those 2 events, if you take 2 with the 4 nodes, you can form that actually doesn't happen, but the static analysis capture that case. So the light gray colored boxes are indicating bugs in our code which were actually capturing statically. So if you take channel 6, you have 3 send statements without any corresponding receive statements, and also no seen events, which means that in that case, if you reach one of those statements, your program is going to stall. And it is important to say that those statements were governed by if statements, so you can execute your program and never reach them. But here, statically, you can capture them. Also, is the corresponding for C8 channel. You have receive statements without any corresponding send statements, and again, the program, if it reaches those statements, it's going to stall. And in the case of event 7, we can see that you have a send and a receive statement happening in the same thread. The compiler was allowing this case, but it's clearly indicating that there is a potential bug there, because it doesn't make any sense having a thread sending and receiving in the same thread. And after we firstly correct all the mistakes that all the bugs that were captured by the first methodology, and then we create again the event interaction graph for the Buggy version in order to test for protocol compliance. So now you create the event interaction graph and you again collect all the feasible scene sequences, and now you can compare them against the one that you have specified in the communication protocol, and you can see test for protocol compliance. It's also important here to demonstrate that a property of the event interaction graph is to capture potential deadlocks in your code. So when you have a crossing event in a synchronous blocking communication model, it's definitely indicating either dead code in your program if you are never reaching a deadlock, or either a deadlock. And as you can see, if you go through thread 3 and you actually take the branch on node 4, then event 5 is going to be executed, and then this is going to stall forever because you didn't reach the node 6, and then this means that this will never go forward to execute those 2 statements. And also, if you never keep that case because you are always taking the branches, then means that this is dead code, and definitely something goes wrong with your program. So what we have done here, we have a new coverage model focusing purely on the communication infrastructure of a message passing program. It complements existing code and functional coverage models. It is important because it can capture static bugs which can be really hidden in your code under if statements, and probably by using conventional code coverage like statement coverage will be very difficult to capture them. Not difficult, it will need a lot of test cases to be sure that you address all those bugs. And you can, as we demonstrate, you can test for protocol compliance by using the scene sequences. And it's important to say that achieving 100% communication coverage requires fewer test cases than 100 conventional code coverage. And the model and the methodologies deployed in this case study are expandable to other programming languages which support message passing, and probably future work is to try them on the MPI paradigm. Thank you.
Thank you. So, do you have any questions? No.
Hi. The environment you developed and presented there is quite a confined environment. What more do you think needs to be done for a more complex environment like MPI?
Yes, it's a good question, because XMOS XC architecture is quite deterministic, so you can predict about a lot of things. We haven't considered yet the complications that will come into when you use something more complex like MPI, or if you even go through loops, because we haven't investigated the cases that you have loops. But then probably you will have to have even more user input to reason about the semantics of the program and get better testability on your program. So probably you will need more user input for the things that are not so deterministic and you can't figure out statically.
Okay, thank you. Thank you.